class. So class is recorded now. Let me make you presenters. 杰豪、秀玉、Darius。好，秀玉、杰。All right. You may start if anyone is ready.
Can you see my screen?
Yes, Jie.
Is question 34 from chapter 6. Suppose x and y are independent normal random variable with parameters mu1, sigma 1, and mu2, sigma 2, respectively. Find x such that p of x minus y is greater than x equal to p of x plus y greater than a for some a. So for the left hand side, we first of all calculate the mu for the x minus 1. That'll be mu1 subtract mu2, and that'll be mu alpha. And for the right hand side, for the x plus y, we have mu1 plus mu2. That'll be mu beta. And for the sigma, we have this. So that's sigma 1 plus sigma 2. And we plug in the formula for the left hand side. We have x minus y plus mu alpha over sigma is greater than x plus mu alpha over sigma. And for, as the end, we got this.
Hold on 1 second. Oh, okay, I got it. Yeah, go ahead. Keep going.
And for the right hand side, we do the same thing, but we use mu beta. And as the end, we got this. And we know those two are equal to each other. So we just solve for x. And then we got this. We expand this. We have the sum of those two. And what's left will be 2 mu1.
Oh, that's why. So for some I see. All right. So this question looks like a difficult question, but it's good. So I have one question. So the variance of sigma is a sigma 1 plus sigma 2 for both cases. For x minus y and for x plus y.
I'm sorry, can I say that again?
Your sigma, the
My
sigma equals to sigma 1 plus sigma 2, right?
Mm-hmm.
For both cases, for x
yes.
minus
so
y, x plus
either
y.
X plus y or x subtract y, or y plus x, y subtract x. We always use the same sigma.
Sigma
so
1
the sign doesn't change anything. So sign only change for the mu.
Okay. All right. Okay, great. Anyone else has any questions? You know, whenever we prove for some number, the question is not easy, but this is done very well. Very nice, Jie. Thank you.
Thank you.
Excuse me.
Question 38. The number of defects in a piece of fabric is Poisson with an average of 2 per square meters. What is A, the probability that there are no defects on 1 square meter of the fabric? From the question asked, we got that lambda will be 2. Then we solve for x equals to 0. Plug into the formulas, we get 0.135. and B, the probability that there are more than 5 defense on 5 square meters of the fabric. For this question, we will do 2 times 5 equals 10 to get the lambda, and then solve for probability of x greater than 5, which is the same as 1 minus probability of x less than or equal to 5. And then plug into the formulas, we get 1 minus 0.0671. Then minus it from 1 to get 0.9329140. And see the accepted number of defense in 2 square meter of fabric, giving that there is 1. We know that the expectation of this distribution is equal to 1, but is equal to lambda. So take lambda squared will be 2 times 2 equal to 4 this time.
Sorry, I mute myself. Okay. All right, nice. Nice. Anyone has any questions? Great. Thank you, Hao. Who's going next?
Quick question. Our homework 6 and 7 was due yesterday, but we're still on chapter 6. I think that was sent a long time ago.
Someone sent me email about that. Right. Sorry, I've been kind of busy these couple of days. Haven't been able to reply any email yet. I would change that. So that's for homework assignments. Chapter 6. What do we have here? Oh, due date in February. Six. Okay, that's okay. So 6, 7, 8, 7. I'm going to put on, so May 19th. May 19th, okay. 8. Excuse me. May 20. Okay, May 20 is okay because our final is on May 23rd. Right. Right. Our final is on May 23rd. Okay. Thank you, Tom. Yeah, I have updated. Thank you. Okay, who's next?
I can go.
Okay.
Can you see my screen?
Yeah.
So I'm going to present 6.44. The joint probability mass function of x and y is given by probability of 1, 1 is 0.9, probability of 1, 2 is 0.04, probability of 2, 1 is 0.03, and probability of 2, 2 is 0.03. So A, compute the conditional mass function of x given y equal to I equal to 1, 2. So in here we use the conditional mass function, which is this. And first I calculate the probability of y equal to 1, which is the probability of 1, 1 plus probability of 2, 1. is equal to 0.93, and the probability of y equal to 2, which is the probability of 1, 2 plus the probability of 2, 2, which is 0.07. So the conditional mass function of x given y equal to 1, which is the probability of x equal to 1 given that y equal to 1, is equal to the probability of 1, 1 over the probability of y equal to 1. And make a calculation which is about 0.9677, and the probability of x equal to 2 given that y equal to 1 is equal to the probability of 2, 1 over the probability of y equal to 1. So it's about 0.0323. And the conditional mass function of x given y equal to 2, which is x equal to 1 given that y equal to 2, is probability of 1, 2 over the probability of y equal to 2. So it's about 0.5714, and the probability of x equal to 2 given that y equal to 2 is probability of 2, 2 over probability of y equal to 2, and it's about 0.4286. And B, x and y independent. So in here we want to show that the joint probability distribution of x and y, if it's equal to the product of their marginal probability, then they are independent. So I first find the probability of x equal to 1, which is the probability of 1, 2 plus probability of 1, 1, and is equal to 0.94. And probability of x equal to 2 is equal to the probability of 2, 1 plus probability of 2, 2, and it's equal to 0.06. And the probability of y equal to 1 and probability of y equal to 2, which we find in A. So use the probability of x equal to 1 times the probability of y equal to 1. It's equal to 0.8742, and the probability of x equal to 2 times the probability of y equal to 1 is equal to 0.0558, and probability of x equal to 1 times the probability of y equal to 2 is equal to 0.0658, and is similar, probability of x equal to 2 times probability of y equal to 2 is equal to 0.0042. And by the question, we know that the probability of 1, 1, which is equal to 0.9, so it's not equal to the answer we find, and other are similar, is all of them are not equal, so x and y are not independent. And C, compute the probability of x minus y equal to 0, and probability of x plus y less than equal to 3, and probability of x over y less than equal to 1. So in here, the probability of x minus y equal to 0, which is 1, 1, and 2, 2. So just plot and just add their probability, which is equal to 0.93, and the probability of x plus y less than equal to 3, which is 1, 1, 1, 2, and 2, 1. So just add their probability is equal to 0.97, and the probability of x over y less than equal to 1, which is 1, 1, 1, 2, and 2, 2. So just add their probability together, which is 0.97.
Right. Tedious work. Thank you. All right, who's next? We have Adarius. Okay.
Okay. So we're looking for the density function for the length of time a machine functions operates effectively as at least 3 of its 5 motors are functioning. So we let xi be the length of time of the ith motor. So we already have given the density function, which is f of x on the problem. And so we compute the CDF for that, for the xi less the event less than or equal to t. And then we take that to get the individual, what's that probability distribution, the f. And then we take that value to get for the given the event of the length of time for the machine functions. We plug that into the that what is that? What is that called? The density function. We compute the density function for the length of time for the total machine functions.
Interesting. Can you explain the last line?
Yeah.
What do you mean?
Line is.
Yeah, you use summation sign. Okay, you go ahead.
Yeah. Yeah, that's it. Because if you're taking the individual mass function from f, and so it's really just it'll be a summation. Given with at least 3 of the 5 motors, so that's with the x equals 3 to 5.
Yeah, I'm trying to understand the question itself. Okay. All right. Thank you, Darius.
Thank you.
Hi, Professor. Good evening.
Yes.
Professor, when you will see the screen, let me know.
Yeah, don't see your screen yet. Oh, yes. Now.
Okay. My question is 15 of chapter 6. If 3 trucks break down at points randomly distributed on a road of length L, find the probability that number 2 of the trucks are within a distance d of each other when d less than equal to L over 2. Define x1, x2, x3 to be random variable that makes the points where these trucks broke down. We have given that the positions of 3 trucks are independent and uniformly distributed over the road. Hence, the joint probability density function is function into xyz is equal to 1 over L cube. We need to find the probability of the event where number 2 points are closer than this d from each other. A base 1 to 3 is equal to x1 plus d less than x2 less than x cube minus d. So event A says that the second truck has broken down more than distance d from the first and the third truck. Similarly, define all other events A like base 1 to 3 and A 1 to 3 and so on. Like we have 3 trucks, so that's why. There are 6 of these events in total. So A is equal to union ijk, A ijk. This is we are going to you can say union of all these 6 events. Probability A into summation ijk probability into A ijk is equal to 6. We have 6 total events. 6 multiply probability into A base 1 to 3. This is our equation 1. Let's find probability into A 1 to 3 and integrate the joint probability density function of appropriate region. So probability into x plus d less than y less than z minus d is equal to integration 0, lower limit is 0 and upper limit is L, which is equal to 1 over L probability into x plus d less than y less than z minus d and dy. So we will separate it, which will equal to 1 over L probability into x less than y minus d probability y plus d less than z dy. So from the question we find that the value of this probability will be equal to y minus d over L. Similarly, L minus y minus d over L dy. So when we solve the integral, so we will get the value 1 over L cube into L cube minus 6 dl square plus 12 d square L minus 8 d cube over 6. So when we will sum up, then we will get 1 over 6 into 1 minus 2d over L cube, because this is the formula of cube. So hence equation 1 yields that probability A is equal to 1 minus 2d over L cube.
Wow. Okay. All right.
Thank you, Professor.
Thank you, Ikera. Thank you. Okay. Okay, ice is up.
Yeah. So I'm presenting question 6.51, and the question asks, consider a sample size of 5 from a uniform distribution over 0, 1, and compute the probability that the median is in the interval 1/4 to 3/4. So in the question, it's given that the sample size is 5 and that the distribution is uniform. So the I values are just going to be 1 through 5. And the median of the sample is 3, so we'd have to apply the density function of third order statistics. And from the chapter, we're given that the density function for third order is n factorial over j minus 1 factorial times n minus j factorial, and then that times the density function times the distribution function to the power of j minus 1 times 1 minus the distribution function to the power of n minus j. And we can see from that that the equation, we first need to compute the density function for the uniform distribution, and we also need to solve for the distribution function, and those just come out to 1 and to x. And with those, we can set up our function, which is the probability that the median x3 is within the interval, and we fill it out accordingly with the bounds and the functions, and we just integrate, and we multiply the equations, and we solve, and the probability that the median is in the interval 1/4 to 3/4 is 0.793.
Nice. Nice job. Thank you, Ice. All right. Okay, so who's left? That's it, right? Everyone went. Oh, Ayat. All right. Let me make you presenter. Okay, Ayat, and anyone else?
Okay, 620. The joint density of x and y is given by the function f of x and y equal to x multiplied by e to the power minus sum x plus y, x plus more than 0 and y more than 0. So I have to check if x and y are independent. And we'll have the second function also, f of x and y equal to 2. Okay, so From textbook, the random variable x and y are independent if for any two sets of real numbers a and b. Probability of x belong to set A and y belong to set B equal to probability of independent probability of x belong to A and y belong to B. So in our case, we have to check that by multiplying f of x and f of y, we get our original function, f of x and y. So firstly, I'll get f of x by differentiation by dy, and I get x multiplied by e to the power minus x. And then I get calculate f of y by using the differential by parts. It equals to e to the power minus e. By multiplying these results, I get our original function, f of x and y. So it means that variable x and y are independent. For the second function, f of x and y equal to 2. Again, I calculate f of x, which is equal to 2, and f of y equals to 2y. By multiplying these two results, I get 4y, which is not the original function, which equal to 2. That means that x and y are not independent.
Nice. Those are nice questions you picked. Thank you. Thank you, Ayat. Okay. Anyone else like to present today? We have 3 classes, I think. Let me just double check. Yes. So I have Thursday, and the next Tuesday, and next Thursday. So 3 classes. If you need to make your presentation grades, credits, you still have time to do that. Okay. So we're skipping chapter 7 because it's not our syllabus. We're going to chapter 8, limit theorem. Okay, limit theorem is one of the actually this okay. 8.1 introduction, 8.2 is a law of large numbers. So the weak law of large numbers. And 8.3, the central limit theorem. 8.4, the strong law of large numbers. So I'm going to check to see if we need to talk about 8.4. So those two, so 8.2, 8.3, 8.4 are the 2 legs of statistics, basically. So we call statistics the science now. Recent 30 years, we started to call statistics science because we have those 2, because statistics have those 2 legs to stand on. Because after internet, so we are able, we have computers, we have these mainstream computers, we can collect enough data. So, okay, let's go for this. So 8.1. All right, so limit theorem. So introduction. Okay, introduction is this much, so let's read. The most important theoretical results in probability theory are limit theorem. Same thing for statistics. All right, the law of large number and the limit theorem. Of this, the most important are those classified either under the heading laws of large numbers or under the heading central limit theorems. So usually theorems are considered to be laws of large numbers if they are concerned with the stating conditions under which the average of sequence of random variables converges, in some sense, to the expected average By contrast, central limit theorems are concerned with the determining conditions under which the sum of a large number of random variables has a probability distribution that is approximately normal. All right. So this is this paragraph, right? So yeah, so the central limit theorem and the law of large numbers. Okay, two big things. 8.2, Chebyshev inequality and the weak law of large numbers. So weak law and comparing to the strong law of large numbers. Okay, we're gonna go to strong law of large numbers maybe later. Let's see the weak one. So Chebyshev's inequality. Let's see the proposition. It's called a marker of the inequality. If x is a random variable that takes only non-negative values from 0 up to infinity, then for any value, positive values, a, probability of x greater than or equal to a is less than or equal to the expected value divided by a. All right, Markov's inequality. So let's see the proof. The proof is, okay, let's define I equals to I or 0 if x is greater than or equal to a, right? Because this probability is calculated under the condition of x random variable greater than or equal to a. 0 otherwise. So since x has to be at least 0, so I, so this one, because I have two values, 1 or 0. Right. So x can be 0. X divided by a has to be greater than I, or I is less than or equal to the random variable divided by a. Taking expectations of both sides, so we have expectation of I less than or equal to expectation of x over a. And what is expectation of I, which that is probability of x greater than or equal to a. And yeah, so that's a little proof. But what's important is just remember the marker of the inequalities. Right? So if x is a random variable, takes only non-negative values, so from 0 above, then for any value, for any positive value a, probability of x greater than or equal to a is less than or equal to the expected value divided by 8. Let's see, second proposition. Second is Chebyshev's inequality. X random variable with a finite mean mu, variance mu square. Then for any value, positive k, probability of absolute value of x minus mu greater than or equal to k. So basically means the values in the neighborhood of such x is less than or equal to sigma squared divided by k squared. So this is called Chebyshev's inequality. So you could think within the radius of mu, right? You have this. The probability of that interval is less than or equal to sigma squared divided by k squared. Let's see the proof. Since x minus mu squared is a non-negative random variable, we can apply Markov's inequality. Right? We can apply this. That is, we can apply this. So probability of x minus mu squared greater than or equal to k squared is less than or equal to expected value of x minus mu squared divided by k squared. Right? So this is use Markov's inequality. And since x minus mu squared is greater than or equal to k squared, if only if x minus mu greater than or equal to k, the absolute value of it, of course. So the absolute value, so probability of the absolute value of x minus mu greater than or equal to k is less than this. And which, what is this? This is just sigma squared divided by k squared. All right, short proof. So, okay. So this is the absolute value of x minus mu greater than or equal to k. Let's read this. The importance of Markov's and Chebyshev's inequalities is that they enable us to derive bounds on probabilities when only the mean or both the mean and the variance of the probability distribution are known. So of course, if the actual distribution were known, then the desired probabilities could be computed exactly, and we would not need to resort to bounds. Okay, so this is, so those two, so a lot of times we won't be able to calculate, right? But we could approximate with its bounds. Let's see examples how we use it. Suppose it's known that the number of items produced in a factory during a week is a random variable with mean 50. So in this case, the mean is given. A, what can be said about the probability that this week's production will exceed 75? B, if the variance of a week's production is known to equal to 25, then what can be said about the probability that this week's production will be between 40 and 60? Right? So we will use the Markovs, we use the Chebyshevs, because this is in between. Okay, A, so let X be the number of atoms that will be produced in a week. A, by Markov's inequality, so X greater than 75, exceeds 75. So that's X greater than 75. So that's Markov's inequality that less than equal to expected value of X divided by 75. Well, expected value is 50. So 50 divided by 75, which is 2/3. Okay. Right. So we won't be able to know exact probability of this, but we know that's less than or equal to 2/3. So we have an upper bound. The second part is by Chebyshev's, right? We have X minus mu, mu is 50, greater than or equal to 10, because it's from 40 to 60, right? 40 is 10 less than 50, 60 is 10 more than 50, so that means the absolute value of X minus 50 is greater than or equal to 10. So by Chebyshev's inequality, that's a sigma squared divided by the k squared. K in this case is 10, so 10 squared. Or sigma is 25. Sigma squared 25. So 25 divided by 100, that's 1/4. So same thing, we have an upper bounds for this. We don't know exactly. We don't have enough information to know exactly, but we can at least have an upper bound for it. A lot of times we cannot calculate exact, but if we're lower bounds, upper bounds, sometimes it's good enough for us. Anyone has any question of this? All right. So that's greater than, right? So this is greater than or equal to 10. So then X minus 150 less than 10 is 1 minus that, is the complement of that. Sigma is 5. Yeah. The variance is a sigma square. So the sigma is 5. Square root of 25. Yeah, so the probability that this week's production will be between 40 and 60 is at least 75%. as Chebyshev's inequality is valid for all distribution of random variable x, we cannot expect the bound on probability to be very close to the actual probability in most cases. Let's see this example. If x is uniformly distributed over the interval 0 to 10, then the expected value will be 5, and the variance, since expected value is 5, and the variance is 25 over 3, it follows from Chebyshev's inequality that x minus 5 greater than 4, that's less than or equal to 25 divided by 3 times 16. 25 over 3 variance, right? Variance divided by 4 squared. Okay, so we know that where this number comes. So 25 over 3 is sigma squared. And the k is 4. X minus mu. So this is k. So k squared is 16. So that's about 0.52. But the exact results can be calculated in this case is x minus 5 greater than 4 is 0.20 because it's a uniform distribution. So you could see those two are kind of far. One is if we use the Chebyshev, so we get 0.52, but to calculate it exactly, that's 0.20. So let's read this. So Chebyshev's inequality is correct. The upper bound that it provides is not particularly close to the actual probability, right? So this is just upper bounds. It can be at most this much, but the exact is this one, because it's kind of far away. But it's not particularly close to the actual probability, so which is sometimes it's like no use. So similarly, if x is a normal random variable with mean mu and sigma variance sigma square, Chebyshev's inequality will be x minus mu greater than 2 sigma less than or equal to 1 over 4. So, the actual probability will be given by x minus mu greater than 2 sigma will be converted into z-score divided, so x minus mu divided by sigma greater than 2, right? Well, just rewrite, just divided by sigma on both sides. But then this will be changed to z-score. So that means that is 2 times 1 minus, checking the table of this, that's about 0.0456. Chebyshev's inequality is often used as a theoretical tool in providing results. So this use is illustrated first by proposition, about proposition. So most important by the weak law of large numbers. So anyway, so this example just to verify this statement. All right, the statement says Chebyshev's inequality is valid for all distributions of random variables x, and we cannot expect the bound on the probability to be very close to the actual probability, okay, in most cases, right? But at least sometimes if we cannot calculate it, give us an upper bound, gives us a cap. Let's see this proposition. If the variance is 0, the probability of x, it will be, the expected value will be 1. Of course, right? Because there's no variance, there's no change among the data. All the data are the same. In other words, the only random variable having variance equal to 0 are those that are constant with probability 1. That's very intuitive, right? But they made a proposition of that. So the proof is by Chebyshev's inequality. Then take the limit of that. Okay, All right, so let's see. The weak law of large number. So I have a sequence of independent and identical distributed random variables, each having finite mean expected value of that one equals to mu. They're all equal to mu. Then for any epsilon greater than 0, probability of the average of these n random variables, the average of the n random variables, subtract the mean absolute value greater than or equal to such epsilon is going to be 0 as n going to infinity. So this is a weak law of large number. What does this mean? This means the average, right? The average just tends to be this mu. Let's see this proof. To be the mean value. So prove the theorem and only under the additional assumption that the random variables have a finite variance sigma squared. Then the expected value of this, the expected average of the n random variables is mu, and the variance is sigma squared. The variance of the average of n variables is sigma squared divided by n. So then it follows by Chebyshev's inequality that the average random value of n variables, subtract mu absolute value greater than or equal to epsilon, is less than or equal to sigma squared divided by n times epsilon squared. Okay. Then when epsilon approaches to 0, then when this approaches 0, when n approaches infinity, the whole thing approaches 0. Usually epsilon is a very, very small number. Okay. So epsilon is a number, very, very close to 0. So this thing as n increase, because it's a law of large numbers. So which means we have enough data, okay, because the random variable represents the data. So as the data set gets enough, big enough, as n goes to infinity, and we use this. So this is a weak law of large numbers. We use this. Actually to prove one of the theory in probability theory, seen also in statistics. See, because the probability theory, we have at least three kinds of probabilities. The first one will be theoretical probability. What is a theoretical probability? Let's say we have two coins, right? We toss the coin, we would calculate, okay, what is the probability to get two heads, right? Get two heads to toss these two coins. And nowadays, with the follow theoretical probability, right? Because getting ahead, we assume getting ahead and getting a tail is all 50%. So this is called theoretical probability. If we just take 50%, 50%. And so we just calculate it theoretically. And another probability is called experimental probability. So we do toss this coin with two coins, and we record each result. Then we only toss twice, and they may not match with the theoretical probability because the the trials are only 2 trials. And the third one is called empirical probability. It's like experience, the probability depends on what happened in the past. So it's like it depends on the experience, depends on, like, if we record for a year, we record the raining days, the sunny days, stuff, we can calculate that. If a random day, it could be a raining day, it could be a sunny day or something. We could, one of the probabilities we can calculate depends on the previous recordings. So that's called empirical probability. But however, why in science or in reality, when we do calculate probabilities, we all follow theoretical probability. We don't follow experimental probability or follow empirical probability because of this law of large numbers. This law of large numbers is saying if you have enough trials, when you raise this n, when the n is big enough, the empirical probability and the experimental probability all converge to the theoretical probability. That's just one of the examples. All right. Okay, that's for today. And the next time we'll talk about central limit theorem and maybe the strong law of large numbers. Actually, let's take a look. What's the difference? Because we have time. The strong law of large number is probably the best known result in probability theory. It states that the average of a sequence of independent random variables having a common distribution will, with probability 1, converge to the mean of that distribution. Oh, okay. Okay, that's what I was talking about. So, okay. Okay, we'll leave this for next time because we still have 3 more classes to go. We have 2 sections. Okay, anyone has any questions? For those of you, you need to earn your presentation credits. We have 3 more classes, so you can present, all right? If you want to present more than 1 time, that's okay. We only have 3 classes now, but you need to choose for different kinds, different types, different kinds of questions to do that. And I want to talk about our final exam. Let me see, someone has questions. Aya is asking theoretical and practical. Oh yeah, practical. Yeah, practical probabilities are the same as frequentist statistics and Bayesian statistics. Frequentist statistics and Bayesian statistics. Oh, I don't know where they call this way. I cannot answer your question because I don't know those 2 statistics. What do you mean by those 2 statistics? Maybe you refer from another class or something, Ayat?
Yes, I remember on one of the class, the professor taught like there are 2 kind of statistics, Bayesian and traditional frequentist.
Oh, okay. What's the course? What kind of course is that?
I don't remember. It was like a year ago. From data science, maybe. I don't know.
Oh, from data science. I see. I see. I guess so. Data science is just such new, science. Such new thing. Okay, they have differentiated all different kinds of statistics now. I didn't know this. Okay, but thank you. Thank you. Okay, so have you seen our final exam date and time? Right here. So final exam, May 23rd, Tuesday, 6 to 8 p.m. Horrible time. Yeah. 8 p.m. is really late in Brooklyn. Anyway, we have to do this. And in Ingersoll building, the room is 3413. All right. So so make sure you bring your pencil. If you need some sketch paper, that's fine. And yeah. Okay, anyone has any questions? So make sure you mark down the final exam date and time and the room number. Oh, you know what? I'm going to delete chapter 7 homework, okay? Because we don't have chapter 7 homework. Let me see. Since it's so late, we should do it online. I wish so too. I don't want to go. I don't want to be out that late in Brooklyn. I'm not familiar with Brooklyn at all. Every time I go to Brooklyn College, I got lost. Let's see other comments. Is there any way we can move the final online since some of us lives far so we get home late? I don't know, because it's a school requirement. Every course has to be on campus. We'll see. The exams are mostly always usually around the same time as class time. I don't know, it's very weird. They should do that. But none of my class have the same time for final exam. It's all messed up. So some of my students in another class, they have 2 exams having the same day, same time. So I send their emails, I forward their emails to the department chair. See, I don't know what to do with this. Anyway, someone lives in India. Catherine, who lives in India or Albany? I think it is to prevent exam. Yes, you are right, Andreli. That's exactly the reason they want to at least one exam, especially typical for final, to be held on campus. Oh, really? Ikera, you live in India? No. Anyway, the education, everything is changing because of COVID. Who knows? One day, we can do online class right now. Before COVID, we wouldn't be able to do this. Who knows? In 2 years, 3 years, 5 years, maybe everything will be online. Because people are saying the next big wave is virtual. Everything go virtual. And Elon Musk sold all his houses, his belongings. He's like, there's no point to have your residence now. Yeah, finance is going to be cumulative, that's for sure. And right, I received an email from the department chair. No reference sheet or notes for final. So which means the questions should be not so challenging. The questions should be basic, just like our exam 1, all right? Yeah, they don't, I don't know, maybe for this course, I'll ask, okay, because I received his email specified for the lower course. For this course, I need to ask him. I will ask. So I'm going to delete homework 7. Am I going to give you a formula sheet? Let me ask the department chair, okay? Yeah, that's a lot to remember. I agree. So let me see if I can delete this directly. Oh, yes, I can delete directly. Okay. So you only have, let's see, 1, 2, 3, 4, 5, 6, 7, 7 homework now. So you have chapter 6 and chapter 8. Chapter 8 is only 3 sections. There are lots of formulas and a lot to use for different questions. Yes, you're right. You're right. Okay, let me ask, all right, to see what I can do, what we can do for the final, all right? Just focus on your homework and your presentation, all right? And I'll answer your questions next class, which is this Thursday, okay?